Welcome to MAT 111, which is Algebra 2 at Suffolk County Community College. I am going to walk you through the notes for Chapter R. I'm going to start with R.1, which is basic concepts. The first thing we're going to introduce is set notation. And to indicate set notation, we are going to use brackets. To start a set and end a set, and inside, when we list the elements of the set, we can either list them in two different ways. This has 3 elements. The number of elements are countable. It makes it a finite set. This has, well, it's showing 3 elements, but ... means it continues in the same pattern indefinitely. So there's an infinite number of elements. This is known as an infinite set. So although we can't write all the numbers down in this set, you know what comes next. 8 comes next, and then 10, and then 12. 2 fourths, those are the even numbers. So let's talk about the types of sets that we're going to see. The first one we're going to see is called the whole numbers. We use a letter W for those, and the whole numbers consist of the elements 0, 1, 2, 3, 4, ... and it continues up and on and forever. Actually, let me let you know about the empty set. The empty set has no elements. How do you list no elements? You could either list it as an empty set of brackets, or you can list it as a 0 with a line through it. This is also known as the null set. Just some terminology for you to remember. Do not write that. Don't write that. That's kind of combining those two symbols. This has one element, and that's just a symbol in that set. That's not the empty set. So do not do that. I'm also put a little, do not do that. So let's take a look at also, I gave you the whole numbers. I made a mistake in not giving you the natural numbers. This is also called the counting numbers. And it is usually, we use the letter N. Don't worry too much about these letters. But this one is almost like the whole numbers. The only thing is, this starts with the number 1. Oops, 2, 3, 4, and then it continues on. So the difference between these two are this has one more, well, it's kind of hard to say. This is an infinite set, this is an infinite set. This one kind of has the extra 0 in it, whole numbers. So you first learn about natural numbers. Count for mommy. 1, 2, 3, 4. I know it sounds silly, but then you get to kindergarten, you realize that you can have 0. So that's the next set that you know about. Let's talk about a variable. A variable is a symbol, usually a letter, used to represent an unknown number or to define a set of numbers. So we can say something along the lines of this. So this says the set of all x, let me just use an example and then I'll write it down for you. X is a natural number between 3 and 10. So we got to think about all the natural numbers between 3 and 10. I'll get to the notation in a minute. So this is equivalent to, so I want to list the natural numbers between 3 and 10. Between 3 and 10 does not include 3. So we'll start with 4. Then we could have 5. Then we could have 6. Then we could have 7, 8, 9, and we cannot have 10. So that's another way to list that, which brings us to set builder notation. Set builder notation. It's how you build a set. So let's say we have kind of what I wrote before, but a little bit more general. So the way you read this is the set of x. This symbol here is such that, and this little piece x has a given property p. So this starts it off, this bracket ends it. So the way you read this is the set of all x such that x has property p. That's how it's written. That's called set builder notation. We're going to see that a lot. This is the piece that might be new to you. So this actually is such that little line, or given. You could write it either way. So let's take a look at using number lines. You have to get very comfortable with a number line. So this is the number line. In the middle here is the number 0, which is neither positive nor negative. Then what we usually do is mark off equal intervals. To the right, these are the positive numbers. And equal intervals to the left of 0. These are the negative numbers. Let me get one more in here. These are the negative numbers. So 0 is pretty much neutral, neither negative nor positive. The numbers to the right of 0 are positive. The numbers to the left of 0 are negative. So this arrow represents that the number line keeps going on and on and on and on. It will continue on until it reaches, actually it never reaches it, but it goes in the positive infinity direction. So that's positive infinity. And the negative continues on until we get in the negative infinity direction. It's like a sideways 8. That's negative infinity. So if you notice, we've already talked about the whole numbers. Whoops, we've already talked about the natural counting numbers. We've already talked about the whole numbers. Our next item to talk about are now the negative side. Those are called the integers. Use the letter I for that. You'll see that more common. And that actually doesn't have a start, but then we pick up a pattern. And then continue the same pattern. So it goes, it's got like two sides of infinity, to the left and to the right. Those are known as the integers. So if we're going to locate 2 on the number line, the number 2 on the number line, that would be this position right here. If we're going to indicate the number -5, that'll be right here. But if you notice, let's look at between 2 and 3. I have a line between them. They're actually, this is 3. Those are the actually counting numbers, but they're also whole numbers and they're also integers. But you need to recognize that there are numbers between these two. You could probably think of one, let's say 2.5 or 2.5. So those are called the rational numbers. So let's see, the rational numbers are basically fractions. Basically fractions. I don't see a letter right now, but we can't list all the fractions. So let's just look between 2 and 3. We've got, I got to think of it as a fraction. So this is 4 halves, this is 6 halves, so 5 halves is right in the middle. 5 halves. If we're looking, let's say 15 fourths. Did I say that right? No, I didn't. I think 9 fourths is 2 1/4. So I can have fractions between any points. Between here, 1/2, 1/3, 1/4, 2/3, 572 over 575. It's like really close to 1, but it's still between there. So the rational numbers are the set of all P over Q such that P and Q are integers. And we have another condition. We always have a problem if we divide by 0, so Q cannot equal 0. Those are the rational numbers. Note, when Q, when Q equals 1, we have the integers. Okay? When Q equals 1, and p is 0, nope, 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 p is positive, we have the natural numbers. So we're going to see a lot of fractions, or also known as rational numbers. What about decimals? Move this up. Decimals and fractions. So basically, any fraction can be written as a decimal by using division. For example, let's say 1 over 2. If you put on your calculator 1 divided by 2, you'll get 1 divided by 2 equals 0.5. What about 1/3? 1 divided by 3 equals, I know what we're going to get. I'm just put it on the calculator so you can see it. You get 0.3333333. It keeps going on and on and on. That's a repeating decimal. So ones that look like this, that kind of stop or end, are called terminating decimals. And ones that keep going are called repeating decimals. So any fraction can be written as a decimal by using division, and it ends up, these fractions will turn into terminating decimals or repeating decimals. I'm sure you've heard about non-terminating, non-repeating decimals. Well, it ends up that, so rational numbers can be written as fractions. Fractions can be written as decimals, terminating decimals or repeating decimals. What about the other ones? Well, those are called irrational numbers. So irrational numbers are decimals that are non-terminating and non-repeating. So it ends up this 0.333333 is not terminating, but it is repeating. So it's got to be both non-terminating and non-repeating in order to be an irrational number. So just, I can't build this in set notation, but there are some examples that we can do. For example, pi. We use the symbol pi. What is that? Let's see. I think this calculator has a pi button. I just have to find it. Oh, there it is. So second pi. I'm going to hit equals, and that's the first few digits of pi. But it ends up that, I could write that down. I don't know this by heart. It ends up, if they've looked at this, about 1 million place values, and they haven't found anything repeating. Some other things that do not repeat. Non-terminating perfect square roots. We'll get into square roots later on and simplifying roots, but like, you know, square root of 1 is 1. Square root of 2, square root of 3, square root of 4. I could keep going. Square root of 4 is 2. But what is square root of 2? That's actually saying what squared equals 2. What number squared equals 2? And this one is saying what number squared equals 3. This one said what number squared equals 4. The answer to this was actually 2. And obviously the answer to this one, what squared equals 1, was 1. So that's why the answer to a square root of 1 is 1 and square root of 4 is 2, because squares and square roots undo each other. So what squared equals 2? Well, you're not going to find a good number for that. But what we could do is we can say the square root of 2, and we can calculate it. It ends up that that number is also non-terminating and non-repeating. 1.414, 213, 562, ... So if I actually plug that in, 1.414213562, and I square it, I'm going to get something close to 2, but not exactly 2. So we're not there yet. There's more digits in that, but it's pretty close to 2. And the square root of 3 is 1.732. 1.732050808 ... I'm saying ... but there is no pattern. It just keeps going. When we do find a pattern, that's when we use the line above the repeating digits. So that's what I mean by non-perfect square roots. 2 is not a perfect square. Whoops, non-perfect squares. I didn't say that right. The square root of non-perfect squares. Wow, I really didn't say that right. The square root of non-perfect squares. The square root of a perfect square, 4, is, so this one's rational. So is this one. And these two in here are irrational. So you'll recognize the perfect squares. And the real numbers equal the set of rational numbers with the set of irrational numbers. This is a union symbol. It's for sets, and it means combine, put them together. Or add them together. So when we went back to the number line that I showed you before is really the real number line. And any number, any real number, can be located on the real number line. Okay, so let's just think of this conceptually. Rational numbers could pretty much put in a magnifying glass and go in and divvy up, let's just look at between 0 and 1, and if I wanted to do eighths or sixteenths or some other combination, I can locate anything in between there. They're irrational numbers. Let's just look between 1 and 2 this time. And this is 1.5. So, you know, square root of 2, it's 1.414, so I'd say it's about here. I could locate it. It's not going to be exact and precise, but that's where it lives. So we know how big it is, but I'm going to have a big magnifying glass, and as we're trying to bounce around and get closer and closer and closer to it, it's going to get more and more precise. That's a little tricky, that one. And let's say here 1.5, and let's say 1.73, and this would be square root of 3. Notice I made a little fat. It's a fat dot. Put it right there. Okay, so take a look on page, let's see, page 4 is the sets of numbers. I walked you through them. You will need to know how to identify which set or sets a number belongs to. And you need to know also the relationship between the sets. So we actually started off the smallest set and we kind of grew larger to the largest set that we talked about, which was real numbers. For now, we'll learn about another set of numbers later on. Let me give you a couple of properties that are also in R.1. The additive inverse property, so basically for any number, let's just say add. So the operation we're using is addition. And inverse means we're undoing. So you have to ask yourself, what undoes addition? But I have to add. So basically I need to add the opposite. What is an opposite? That's the negative of the number. So what do we say? So what happens when we have 5 and we add -5? What do we get? Well, we end up with 0. And it ends up 0 is the additive identity. Additive identity. Or we can say that so we'll say A plus -A equals 0. That's the additive inverse property. We can also say that a number plus 0 will get us the same number back. Adding 0 doesn't add anything, so we get the same number back. That's actually called the, I don't know if it's got a property, but this is the additive inverse. I'm sorry, additive identity property. So what is this? Wait, what do I do here? So if I have negative 7, what do I need to add in order to get to 0? Well, I need the opposite of negative 7. And what's the opposite of negative 7? The opposite of negative 7 is the negative of the number. That's what that's saying, is actually positive 7. So I need to put in a positive 7 here. And so we show the property, the additive inverse property, when we have a negative number. Let me start with a negative number. Okay. Absolute value. Absolute value. So the absolute value of a number is the positive distance from 0. I'm not too crazy about that, but let's just take a look at what it is. The absolute value of negative 5 is just 5. The absolute value of positive 7 is just 7. The absolute value of negative 715 over 432 is, well, that's just 715 over 432. Notice how once I do the absolute value, I get rid of those bars. So you can write this using kind of a set notation. It would look like this. The absolute value of A equals, it'll equal positive A, or it will equal negative A. Now, it depends. If it stays the same, that means A is positive, or 0, right? And it actually is the opposite. When this has to be positive. If this is going to be positive, then what I started with, I need to change the sign. So what I started with must have been negative. I think this notation complicates the situation, but we're going to see a lot of absolute values later on. So there are some examples we can go through. And for instance, well, what about the absolute value of negative 8? That's just 8. But what about the negative absolute value of negative 8? So we've already seen that this piece here is positive 8. But I didn't take care of this one out front. So negative 8. Look at the difference here. Negative 8. Well, what's the opposite of 8? Well, that's just negative 8. So I want you to see the difference between these two. Got to evaluate absolute value of negative 8 and then take the opposite of that. Did I say that right? You have to evaluate the absolute value of -8 and then take the opposite of that. So it's the opposite of +8 is -8. We are not even done with R.1 yet. Let's take a look at some inequality symbols. Take a look at some inequality symbols. So we have, well, we have this symbol, which means less than. We have this symbol, which means greater than. And if we take a look at how to make these true, the smaller number is always to the left of the bigger number, I'll say the larger number, on the number line. Also, when it comes to the symbols, this one is L less than, and this one's greater than. It always faces towards the smaller number. So I'll put that in parentheses, the arrow always points toward the smaller number. Or the mouth always points toward the larger number. You might have seen this as Pac-Man, so some people have seen that. So let's say here, let's put in the correct symbol. And having a number line might actually help you. This is the 5. And this would be a -5, and you kind of keep going. We could see what we need. Let's take a look at 8 and 9. So 5, 6, 7, 8, 9. 8 is actually less than 9. What about -6 and 15? Well, -6 is all the way down here, and 15 is all the way up here. So -6 is less than 15. Notice how that's smaller, so it's pointing to it, or it's actually eating the bigger number. What about 7 and 0.5? So 7 is all the way up here. 0.5 is positive, so it's on the right-hand side, but it's right here. So 0.7 is greater than 0.5. You know, I don't like how I've got, made that a blank, but it looked like less than equal to. Make it like that. And then I'll leave them out. What about 0 and -572? Well, where's 0? 0 is right here. Where is -572? That's all the way down here. So it ends up, that's the smaller one. So it gets the arrow. So this says 0 is greater than negative 572. Think about where they're located on the number line. So we can say that A less than B if A is to the left of B, and A is greater than B if A is to the right of B. It's kind of forcing. It's pointing to the right. So you'll need to know how to locate numbers on a number line, and determine inequality. The inequality sign between two numbers. These two go hand in hand. And that's the end of R.1.